Okay, welcome everyone. So in this video, I want to return back to the invertible matrix theorem that we saw earlier this semester. And now that we've talked about the dimensions of the subspaces of a matrix, namely the null space and the column space, what we call the nullity and the rank of a matrix, we can add on even more equivalent statements to the invertible matrix theorem. So statement A of the theorem is that A is an invertible matrix. And then we have a long list of equivalent statements, meaning that if statement C is true, A has n pivots, then that means A is invertible, and vice versa. If A is invertible, then that means A must have n pivots. And now we can add some additional equivalent statements using what we know about the column space and the null space of a matrix. So the first additional statement that we can add, which is going to be equivalent to all of the other statements in the invertible matrix theorem, would be that the columns of matrix A form a basis for Rn. And so if A is an n by n matrix, recall that the column space of matrix A is going to be a subspace of the number of columns, which would be n. So the column space of matrix A is a subspace of Rn. And if A has n pivots, the column space of matrix A is going to have a dimension, a rank, which is equal to the number of pivot columns. So if we have n pivot columns, that means the column space of matrix A is going to span the entirety of the codomain, which is all of Rn. And so very much related to this statement M, this is equivalent to saying that the column space of matrix A is equal to Rn. It's the entirety of the codomain. And this is equivalent to saying that the rank of matrix A is n, since any basis for a space which is equal to Rn would have to contain exactly n elements. And then using the rank theorem, we know that the rank of A plus the nullity of matrix A should equal the number of columns n in matrix A. And so if the rank is n, then this would tell us that the nullity, therefore, would be equal to 0. And there's only one subspace that has nullity 0, and that would be the subspace that consists of just the 0 vector. And you can check that some of the other earlier statements that we had for the invertible matrix theorem, one of them was saying that the equation AX equals 0, this has just the trivial solution. So this is clearly equivalent to saying that the null space of A just consists the 0 vector. So we have tons of equivalent statements, tons of ways of determining whether or not a matrix A is invertible.